There is a moment when a number on a screen stops being weather and becomes something closer to a diagnosis. In Baghdad, that moment arrives near 50 degrees Celsius. In Phoenix, it arrives near 46. In London, a city built of brick and stone for a cool, damp climate, it arrives at 35. Because London was never designed to survive what is now landing on it every few summers. Right now, in laboratories, weather stations, and ocean buoys scattered across 6 continents, instruments are recording numbers that did not used to exist in the historical record. Climate scientists, who spend their careers being cautious with language, are increasingly choosing words they once avoided. This is not a forecast about a distant decade. This is a description of what has already been measured, already logged in hospital admissions, already visible in crop yields, already written into temperature records that stretch back more than a century. Heat used to be background noise, the thing that made people reach for a fan or a cold drink. It has become something else entirely. A force that is rewriting how food is grown, how water is distributed, how cities function, and where on this planet it remains physically possible to live and work. To understand why, it helps to start with the body, because the body is the most honest instrument we have. Human physiology operates inside an extremely narrow band. Core temperature sits close to 37 degrees Celsius. At 38, the body registers fever. At 40, physicians call it severe hyperthermia. Above 41, tissue damage begins. Past 42, certain proteins inside human cells start to lose their structure permanently, a process with a precise biochemical name: denaturation. This is not rhetorical exaggeration. It is measurable chemistry. The same kind of chemistry that happens when an egg white turns solid in a hot pan. The body's main defense is evaporative cooling, sweat lifting heat away as it turns to vapor. That defense only works if the surrounding air is dry enough to absorb moisture. This is why extreme dry heat, even at 45 or 46 degrees, can sometimes be survived with shade and water, while a far lower temperature combined with high humidity can be lethal within hours. When the air is already saturated with moisture, sweat simply sits on the skin. It stops evaporating. The body keeps generating heat from the inside with no way to release it. Scientists describe the danger point using a measurement called wet bulb temperature, a single number that folds heat and humidity together into one physiological threshold. Once wet bulb temperature reaches roughly 35 degrees Celsius, even a healthy person resting in the shade with unlimited water cannot keep their core temperature stable. Not for 1 hour, not for 2, not at all, for as long as those conditions persist. For decades, climatologists treated this threshold as a theoretical ceiling, something the planet's actual weather would never reach in places where people live. That assumption no longer holds. Instrument readings near the Persian Gulf coastline and in parts of South Asia have already brushed against this limit. For short windows, in specific locations, but recorded nonetheless. Climate projections built from decades of satellite and ground data suggest these windows will widen, spread across larger areas, and arrive more often as the planet's average temperature continues to climb. Cities deserve particular attention here, because a city is not simply a place where people happen to live. It is a machine that manufactures its own extra heat. Dark asphalt absorbs solar radiation instead of reflecting it. Concrete holds that heat and releases it slowly through the night. Glass towers bounce sunlight downward into the spaces where pedestrians walk. Buildings packed close together block the wind that would otherwise carry heat away. Trees and grass, which cool the air through evaporation, are often scarce in the densest urban cores. Air conditioning units cool interiors while pumping their waste heat directly into the street. Taken together, this is what researchers call the urban heat island effect, and field measurements from cities on nearly every continent show a temperature gap between a city center and the surrounding countryside that ranges from roughly 2 or 3 degrees in smaller, greener towns to as much as 8 or 9 degrees in the densest megacities with minimal vegetation. In practical terms, a rural thermometer reading 36 degrees can correspond to a downtown reading above 44. A reading of 41 outside the city can mean 49 inside it. The people most exposed to that gap are often the people least equipped to handle it. Elderly residents in older apartment blocks without cooling, families in informal settlements built without any consideration for heat, workers who cannot simply retreat indoors. Phoenix, Arizona offers one of the clearest illustrations of what sustained extreme heat does to a major metropolitan population. The city has experienced consecutive summers in which the number of days above 43 degrees Celsius has set new records year after year. Local health authorities track heat-related deaths with increasing precision, and the toll has climbed sharply over recent years, concentrated overwhelmingly among people experiencing homelessness, the elderly living alone, and people with chronic illness who lack reliable access to cooling. Emergency rooms report seasonal surges of heat stroke cases that strain staffing during the hottest weeks. None of this is modeled or projected. It is recorded in county medical examiner reports year after year, with the numbers moving in one direction. Climatologists who monitor this data do not speak in terms of whether such events will continue. They speak in terms of how much worse they expect the coming decades to be. Now, consider water, because heat and water are bound together in ways that touch nearly every basic human need. Extreme heat accelerates evaporation from lakes, reservoirs, and soil. Mountain snowpack that normally melts gradually through the warm season instead melts earlier and faster, front-loading river flow into spring and leaving rivers thinner during the peak of summer demand. Groundwater recharges more slowly because parched soil sheds rainfall instead of absorbing it. The Colorado River Basin in the western United States illustrates this with stark clarity. Lake Powell and Lake Mead, the two largest reservoirs on the river, have both dropped to historic lows within the same decade, exposing rings of pale mineral deposit on their banks that mark where the waterline used to sit years earlier. Hydropower generation at the dams that depend on these reservoirs has had to be curtailed as water levels approached the minimum needed to keep turbines running. 7 U.S. states and dozens of tribal nations depend on this river system, and water allocation negotiations that once felt routine have become genuinely contentious because there is measurably less water to allocate. A comparable story has played out along the Yangtze River in China, where a severe drought combined with extreme summer heat caused water levels to fall so low that sections of the river became difficult to navigate. Hydropower output dropped sharply during a period of peak electricity demand for cooling, and some factories in affected provinces were temporarily ordered to reduce operations to preserve power for residential use. For economies that rely on river transport and hydroelectric generation, this is not an abstract inconvenience. It is measured in billions of dollars of disrupted production and shipping delays. Heat also changes water quality, not only its quantity. As surface water temperatures rise, certain waterborne pathogens find more favorable conditions to multiply, including bacteria responsible for serious respiratory infections that thrive in warm water systems, particularly in plumbing and cooling towers that were engineered decades ago for a cooler climate. Utilities in several countries have had to increase monitoring and adjust treatment protocols specifically during heat waves, an adaptation that did not exist as standard practice a generation ago. It is not evidence that engineers made mistakes when these systems were built. It is evidence that the climate those systems were designed for no longer matches the climate that now exists. Food security is where heat becomes intensely personal for billions of people, because heat changes what grows and how much of it survives to harvest. Wheat, rice, corn, and soybeans each have a narrow temperature window during flowering and grain formation, and exposure to extreme heat during that specific window can devastate a harvest that looked healthy just days earlier. India, one of the world's largest wheat producers, experienced a punishing early heat wave that arrived precisely during the flowering period of its wheat crop, an event severe enough that the government restricted wheat exports to protect domestic supply, sending ripples through global grain markets that depend on Indian wheat. Countries that rely on imported grain from parts of North Africa to Southeast Asia felt the effect in rising bread prices within weeks. Coffee tells a similar story in a different crop. Arabica coffee, grown across the highlands of Brazil, Vietnam, and Central America, is acutely sensitive to heat stress during flowering, and prolonged periods above its tolerance threshold reduce both yield and bean quality. Several major coffee-growing regions have reported declining harvests linked directly to hotter, drier growing seasons. And some growers are already relocating plantations to higher elevations in search of cooler microclimates, an adaptation that takes years to establish and carries real financial risk. Rice paddies across South and Southeast Asia face a parallel threat, since rice yields drop measurably once nighttime temperatures during the grain filling stage rise above a critical threshold, and warming nights, not just hotter days, are increasingly common across the region's major rice basins. Livestock feel heat stress just as directly. Dairy cows redirect metabolic energy away from milk production and toward simply regulating body temperature once ambient heat and humidity cross a certain combined threshold. And milk yields across multiple dairy-producing regions have shown measurable seasonal declines tied to hotter summers. Poultry are even more vulnerable, since chickens lack sweat glands and cool themselves almost entirely through respiration, an inefficient mechanism in humid heat. Mortality on poultry farms rises sharply once temperatures climb past roughly 38 degrees, even with mechanical ventilation running, and producers in several regions are now investing in evaporative cooling systems that would have seemed unnecessary for their climate only a decade ago. The ocean holds the key to understanding why all of this is accelerating faster than older climate models anticipated. More than 90% of the excess heat trapped by greenhouse gases over the past several decades has been absorbed by the world's oceans, acting as an enormous buffer that has kept the atmosphere from warming even faster. That buffer is neither infinite nor free. Sea surface temperatures have repeatedly broken records in recent years, and in some regions of the North Atlantic and the tropical Pacific, anomalies of several degrees above the long-term average have been recorded. an extraordinary deviation for a system that normally changes with the inertia of an ocean basin rather than the volatility of weather. Warmer ocean water is fuel for tropical cyclones. Storms draw their energy from the heat stored in the upper layers of the sea, and warmer water allows storms to intensify more rapidly and reach higher peak intensities. Meteorologists tracking recent hurricane and typhoon seasons have observed that while the total number of storms has not changed dramatically, the proportion reaching the most extreme intensity categories has increased. And this shift correlates directly with rising sea surface temperature in the basins where these storms form. Coral reefs translate ocean heat into one of the most visually dramatic forms of ecological loss on the planet. Reefs cover a tiny fraction of the ocean floor, yet support an estimated quarter of all known marine species at some stage of their life cycle. Coral polyps live in partnership with microscopic algae that supply most of their energy through photosynthesis. When water temperature rises even 1 or 2 degrees above the local seasonal norm for a sustained period, these algae begin producing compounds toxic to their coral hosts, and the coral expels them, leaving behind a bleached, bone-white skeleton. If the heat stress continues for more than a few weeks, the coral dies outright. The Caribbean experienced a mass bleaching event severe enough that researchers documented coral mortality across reef systems, from the Florida Keys to Belize, within a single season. An event many marine biologists described as among the most severe regional bleaching episodes ever recorded for that basin. Marine heat waves, a term that entered common scientific use only because the phenomenon itself became frequent enough to need a name, are now tracked in real time by oceanographic agencies, and the proportion of the global ocean surface experiencing one in any given year has trended upward for decades. Along parts of the eastern Pacific, a prolonged marine heat wave devastated underwater kelp forests, vast ecosystems that had supported commercial fisheries for generations. Fishing communities that had worked the same waters for decades reported catches collapsing within a few seasons, an economic shock traced directly back to a shift of only a few degrees in water temperature at depths most people never see. The Arctic explains why heat in temperate latitudes has become so erratic. The region is warming between 2 and 4 times faster than the global average, a disparity that is reshaping the very system of winds that normally keeps cold air locked in the high north. The polar jet stream depends on a sharp temperature difference between the Arctic and the mid-latitudes to stay strong and stable. As that difference shrinks, because the Arctic is heating so much faster than everywhere else, the jet stream weakens and becomes more wavy, more prone to large meanders that stall in place instead of moving steadily from west to east. Meteorologists call a stalled high-pressure system that traps a mass of hot air over one region for an extended period atmospheric blocking. And blocking events are the mechanism behind the most dangerous heat waves, the kind that last not for a single afternoon, but for 2 or 3 relentless weeks, never giving the body or the power grid time to recover. A severe blocking event in recent years drove temperatures across parts of Western Europe to levels that broke national records by wide margins, including readings above 40 degrees in places like parts of the United Kingdom that had essentially never recorded such heat before. Researchers using a relatively new branch of climate science called attribution science calculated how much more likely this specific event became because of human-driven climate change compared to the climate of a century ago, and found the probability had increased many times over, transforming what would once have been an essentially impossible event into something that can now recur within a human lifetime. Scientific teams now routinely publish this kind of attribution analysis within days of a major heat event, giving the public a quantified answer to a question that climatologists once considered unanswerable, namely, whether a specific extreme event can be tied to climate change at all. Outdoor workers stand at the front line of this shift every season in every hot region of the world. Agricultural laborers across South Asia often begin work before sunrise, specifically to finish as much as possible before the worst of the afternoon heat. Yet even pre-dawn temperatures during peak summer can already exceed 30 degrees in some regions, leaving the body little time to recover overnight before another day of exertion begins. Heat stroke among field workers is documented routinely by local clinics during the hottest months, not as a rare event, but as a recurring seasonal statistic. Construction workers across the Gulf states face conditions severe enough that several governments have implemented mandatory midday work bans during the hottest months of the year, shifting construction schedules to early morning and night. A structural change to an entire industry driven directly by what the climate now demands. Research conducted across multiple outdoor labor sectors in South and Southeast Asia indicates that productivity for physically demanding outdoor work drops substantially once wet bulb conditions cross certain thresholds, a measured physiological response rather than a subjective complaint of fatigue, since the body involuntarily slows its own pace to avoid overheating. The International Labor Organization has estimated that heat-related productivity losses already cost the global economy hundreds of billions of dollars annually in lost working hours, concentrated overwhelmingly in tropical and subtropical regions where outdoor labor remains a large share of total employment. A chronic kidney disease of unclear origin has been documented for years among agricultural workers in parts of Central America, particularly those laboring in sugarcane fields under direct sun for long hours. The condition disproportionately affects young, otherwise healthy men with none of the typical risk factors for kidney disease, such as diabetes or hypertension. After extensive research, the leading hypothesis links the disease to repeated episodes of severe dehydration and heat stress that, over years of accumulation, cause irreversible kidney damage. A single dehydration episode causes temporary kidney strain that the body can usually recover from. Repeated across season after season, the damage compounds and becomes permanent. Researchers studying similar patterns among outdoor laborers in the Middle East and parts of Africa suspect the mechanism may not be confined to one region or one crop, but rather reflects what sustained occupational heat exposure does to the human body over years of repetition. Children experience heat through a different physiology than adults, and that difference matters. A child's ratio of skin surface area to body mass is larger than an adult's, which means children absorb and lose heat faster. The systems that regulate body temperature are not fully developed before roughly age 3, and very young children often cannot communicate discomfort until symptoms are already severe, nor can they independently find water, shade, or remove excess clothing. Pediatric emergency departments in cities across India and Pakistan report sharp increases in admissions for heat exhaustion, severe dehydration, and heat-related seizures on days when temperatures exceed roughly 42 degrees. Increases that in some hospitals exceed a quarter above baseline admission rates on ordinary days. Several countries now close schools during extreme heat events, a decision driven by the fact that classrooms without cooling can become hotter inside than the air outside, because heat absorbed by roofs and walls has nowhere to escape. Playground equipment has become an unexpected hazard in its own right, since metal slides and railings exposed to direct sun can reach surface temperatures of 60 to 70 degrees, hot enough to cause skin burns within seconds of contact. Pediatricians in several countries, including parts of Australia and the southern United States, have documented burn injuries from playground equipment, prompting updated safety standards that now require shade structures and heat-resistant materials in new playground construction. Older adults remain the population most consistently lost to extreme heat, and the reasons are rooted in basic cardiovascular physiology. A severe and prolonged heat wave across Western Europe years ago, with nighttime temperatures that never dropped below roughly 24 degrees and daytime highs regularly above 38, produced an estimated excess death toll in the tens of thousands across the continent, concentrated overwhelmingly among elderly people living alone, often on upper floors of buildings without air conditioning, where heat accumulates most severely. That death toll did not arrive as a single dramatic event. It accumulated day after day, largely unnoticed in real time, only becoming visible afterward when public health agencies compared the period's mortality figures to historical averages. The physiological chain behind many of these deaths rarely looks, on paper, like death from heat at all. Dehydration thickens the blood. A thicker, more viscous bloodstream forces the heart to work harder to circulate it. Blood vessels near the skin dilate in an attempt to release heat, which can cause blood pressure to drop sharply. In an elderly person whose cardiovascular system already operates with reduced reserve capacity, this combination can trigger a fatal cardiac event. The death certificate typically records heart failure, not heat, and the connection to the heat wave is never formally noted. This is precisely why epidemiologists rely on excess mortality, comparing total deaths during a heat event to the number that would normally be expected for that time of year, rather than relying on death certificates alone. The gap between those two figures is the true cost of a heat wave, and across multiple countries, that gap has been trending upward. In response to that earlier European heat wave, France built a national heat response plan with graduated alert levels, activating social outreach services, opening public cooling centers, and mobilizing emergency medical resources as temperatures climb. That plan, once considered an exceptional emergency measure, now activates almost every summer as a matter of routine. A quiet but telling indicator of how much the regional climate has shifted within a single generation. Spain, Portugal, Greece, and Italy, countries long accustomed to hot summers, have each recorded national temperature records in recent years that exceed anything in their historical archives, with multiple readings above 45 degrees in Spain and a provisional European record approaching 49 in Sicily. These are not records celebrated for their own sake. They function as markers of where the regional climate is heading. Nighttime heat is an aspect that receives far less public attention than daytime extremes, despite its outsized medical significance. The human body relies on a drop in core temperature of roughly 1 degree overnight to trigger restorative processes, including immune system activation, cardiovascular recovery, and the consolidation of memory during sleep. When overnight air temperature fails to drop below roughly 25 to 27 degrees, a threshold researchers label a tropical night, the body cannot cool sufficiently, and that overnight recovery does not occur in full. One such night produces mild discomfort. A run of consecutive tropical nights produces accumulating physiological stress, and for an elderly person managing chronic illness, a week of tropical nights represents a genuine health risk rather than mere inconvenience. The frequency of tropical nights has risen measurably across most regions of the world over the past half-century, clearly visible in long-running weather station records. Cities across southern Europe that cooled overnight to roughly 18 or 19 degrees just 3 decades ago now regularly record nighttime lows above 27 or 28 during heat events. For the majority of the world's population without air conditioning, tropical nights translate directly into sleep deprivation, accumulating fatigue, and rising health risk, which is part of why several European governments have begun subsidizing cooling units specifically for low-income elderly residents, not as a comfort measure, but as a public health intervention. Air conditioning itself carries an under-discussed paradox worth examining honestly. It cools indoor air by expelling heat outdoors, a negligible effect at the scale of a single building, but a measurable one at the scale of an entire city running millions of units simultaneously. Research in several major Asian cities has found that widespread air conditioning use adds a measurable amount, roughly 1 to 2 degrees, to nighttime air temperature in dense urban districts. This creates a feedback loop. The hotter it gets outside, the more air conditioning runs, and the more air conditioning runs, the hotter the immediate outdoor environment becomes. At the same time, air conditioning draws enormous amounts of electricity, with peak demand concentrated precisely on the hottest days, exactly when power grids are already under the most strain. Electricity grids and extreme heat form a story of systemic vulnerability that most people only notice when the lights go out. Heat drives a surge in electricity demand as air conditioners, fans, and refrigeration units all run harder simultaneously, creating peak loads that can far exceed average demand. At the same time, heat reduces the efficiency of the grid itself. Power lines sag as metal expands, reducing clearance above the ground. Transformers and substations overheat, losing efficiency in heat exchange. Thermal power plants that rely on river water for cooling face a particular constraint, because during droughts and heat waves, rivers run lower and warmer, and many environmental regulations prohibit discharging cooling water back into a river once it exceeds a certain temperature, since that discharge would damage the river's ecosystem. Several nuclear plants in France have had to reduce output or temporarily shut down for precisely this reason during severe summer heat. The result is a dangerous mismatch. On the very days when electricity demand peaks, the grid's capacity to generate and deliver that electricity comes under simultaneous strain. This combination has already triggered widespread blackouts in multiple regions of the world, and a blackout during a heat wave is not a mere inconvenience. It is a medical emergency for vulnerable populations, since losing ventilation or refrigeration during extreme heat can be life-threatening within hours for elderly residents or anyone managing a chronic illness. Heat's effect on the human mind receives less attention than its physical toll, yet the evidence is substantial. Multiple independent studies across different countries and time periods have found a measurable statistical correlation between rising temperature and increased aggression, including spikes in roadway conflicts, domestic disputes, and reported incidents of interpersonal violence. The proposed mechanism involves heat's effect on the brain's prefrontal cortex, the region responsible for impulse control, weighing consequences, and rational decision-making. Heat elevates cortisol, the body's primary stress hormone, and disrupts sleep, which is itself a critical factor in emotional regulation. When heat persists for weeks without nighttime relief, it produces a state of chronic stress that erodes psychological well-being over time. Several studies conducted in parts of Asia and North America have documented statistically significant increases in psychiatric hospital admissions during prolonged heat events, spanning depression, anxiety disorders, and the worsening of existing chronic mental illness. Researchers working in this area describe it as one of the least studied and least discussed dimensions of how heat affects human beings, precisely because the physiological mechanisms are far better understood than the psychological ones, which is why this area of research has expanded considerably in recent years. Sleep deserves separate attention, because sleep is not a luxury but a biological necessity that heat directly undermines. A drop in core body temperature of roughly 1 degree is required to trigger the release of melatonin and the transition into sleep. When ambient air remains too warm, the body cannot cool sufficiently. Falling asleep becomes harder, and the sleep that does occur is shallower, with restorative processes left incomplete. A large-scale study using data from wearable sleep tracking devices across millions of users found that each additional degree of nighttime warmth was associated with a measurable reduction in average sleep duration. That reduction sounds minor on a single night, a matter of a few minutes, but accumulated across hundreds of nights, it represents a genuine chronic sleep deficit. And chronic sleep deprivation is independently linked to elevated cardiovascular risk, weakened immune function, increased diabetes risk, and reduced cognitive performance. Cognitive performance and heat intersect in ways with real economic consequences that are rarely discussed in climate terms. A study conducted at a major American university tracked cognitive test performance among students living in dormitories without air conditioning during a heat wave, comparing their results to students in cooled buildings nearby. The non-cooled group scored measurably worse on tests of attention, working memory, and arithmetic speed. A notable difference given that these were young, healthy individuals who were not engaged in physical labor, simply living and studying in a warm room. Office workers without adequate cooling show measurable productivity declines once indoor temperatures exceed roughly 26 to 27 degrees, an effect that, multiplied across hundreds of millions of workers and weeks of seasonal heat, represents an enormous, difficult to tabulate, but entirely real loss of economic output. The economics of heat translate the climate problem into figures that governments and corporations are forced to take seriously. Direct losses include agricultural damage from reduced yields, livestock losses, destroyed orchards and vineyards, wildfire damage to homes and infrastructure. The cost of medical response, including hospitalizations and ambulance services, and losses from power outages and transportation disruptions. Indirect losses include reduced labor productivity, rising household spending on cooling, and increasing insurance costs in regions classified as high climate risk. The International Labor Organization estimates that heat stress already costs tropical regions of the world a substantial share of total working hours annually, a loss measured in the trillions of dollars globally each year. Major financial institutions, including the World Bank and the International Monetary Fund, now incorporate climate risk, with heat increasingly treated as a primary factor, into their assessments of national economic outlooks, a shift that affects credit ratings, investment decisions, and long-term development planning, no longer treated as an environmental side issue, but as a core economic risk factor. Wildfires are perhaps the most visually dramatic expression of extreme heat, because fire requires three things: fuel, oxygen, and an ignition source. and heat improves the availability of all three simultaneously. Vegetation dries out within days under extreme heat, becoming flammable at moisture levels that would have been safe a decade earlier. Winds often intensify during heat events. Ignition sources, lightning, power lines, sparks from machinery or vehicles, are a constant background risk. Satellite monitoring shows that fire seasons across most fire-prone regions of the world have grown measurably longer compared to several decades ago. The area burned annually in places including Australia, Siberia, California, Canada, and the Mediterranean has repeatedly set records that were then broken again within just a few following seasons. Devastating wildfires on the Hawaiian island of Maui, driven by extreme dryness and high winds, destroyed a historic town and killed more than 100 people. A tragedy that surprised many precisely because it occurred in a tropical location not traditionally associated with severe fire risk. Catastrophic fire seasons in Canada in recent years sent smoke plumes thousands of kilometers across the continent, demonstrating that extreme wildfire risk is no longer confined to regions that have always expected it. Soil itself undergoes changes during sustained extreme heat that are rarely discussed, yet carry consequences stretched across years. Extreme heat accelerates moisture loss from topsoil through evaporation far faster than under normal conditions. Clay-heavy soils contract and crack as they lose moisture, and once that structural damage occurs, the soil loses its capacity to retain water at all. The next rainfall does not soak in, it runs off the surface instead. This creates a self-reinforcing cycle. Heat dries the soil, dried soil rejects rainfall. Rainfall runs into rivers instead of replenishing groundwater, and the next heat wave finds even less moisture reserve to draw on. European drought monitoring agencies that track soil moisture using satellite and ground-based data have reported a year-over-year increase in the area of the continent classified under extreme soil dryness. Farmers across the Iberian Peninsula are now making decisions that did not exist as options for their parents. Drilling new wells despite falling groundwater tables, switching to drought-tolerant crop varieties despite uncertain market demand, or abandoning land that families had farmed for generations. Climate-related migration does not begin at some defined temperature threshold. It begins at the point where staying becomes economically impossible or physically unbearable. In parts of Bangladesh and India, farming families are relocating to cities not out of any preference for urban life, but because agricultural labor during summer heat has become too unpredictable, harvests too unstable, and irrigation water too expensive. Similar internal migration, not yet formally classified as climate migration, but driven by precisely the same underlying causes, is occurring in parts of Central Asia, coastal regions of South Asia, and arid zones across sub-Saharan Africa. The World Bank has estimated in multiple analyses that climate-driven migration could affect well over 100 million people in the most vulnerable regions of the world by mid-century, not as a single dramatic wave, but as a gradual, accumulating process whose earliest signs are already visible in demographic data. International refugee law does not currently recognize a legal status for people displaced specifically by climate conditions, a gap in international policy that is increasingly discussed at global forums, without, so far, a concrete resolution. Wild animals cannot simply turn on a fan, and their response to extreme heat offers a biological indicator anyone can understand. In Australia, a severe heat event caused thousands of flying foxes, large fruit bats, to die within a single afternoon, found beneath their roosting trees, because temperatures above roughly 42 degrees proved fatal within hours. This was not a gradual decline. It was an acute event that erased populations built up over years in a single day. Seabirds nesting on exposed tropical atolls face a comparable threat, as chicks overheat in their nests during extreme heat, and adult birds standing over them with wings spread for shade cannot always compensate once temperatures cross a certain point. Researchers have documented mass chick mortality during heat events severe enough to erase entire breeding seasons for some colonies. Pollinating insects represent a quieter but economically significant casualty. Honeybees redirect their effort from foraging to hive cooling once ambient temperatures exceed roughly 35 degrees, fanning the hive with their wings and carrying water to evaporate inside it rather than collecting nectar and pollinating crops. Roughly a third of the food humans eat depends on insect pollination, including almonds, apples, cherries, berries, and a wide range of vegetable and oilseed crops, all of which require pollination during a narrow flowering window. If a heat wave coincides with that window, yields fall, regardless of how healthy the plants themselves are. Beekeepers in California, Spain, and India have already reported reduced honey production and pollination activity tied directly to abnormal heat events, a problem that surfaces months later as smaller harvests on store shelves. Physical infrastructure absorbs extreme heat in ways most people never consider until something fails. Asphalt begins to soften once surface temperatures exceed roughly 50 to 55 degrees, reducing its load-bearing capacity. And heavy vehicles have visibly rutted road surfaces during extreme heat events in parts of South Asia. Railway tracks expand when heated, and if that expansion exceeds the rail's design tolerance, the track can buckle, a failure engineers call a sun kink, which creates a derailment risk. Rail operators in several countries impose speed restrictions during extreme heat specifically to reduce the mechanical stress a moving train places on the rails. Bridges are engineered with expansion joints calibrated to a specific temperature range, and when temperatures exceed that range, those joints operate at the edge of their design tolerance, prompting engineers to revise structural standards to reflect a climate that no longer matches the one the original designs assumed. Aviation has a less obvious relationship with heat that affects flights most travelers never connect to climate. Aircraft generate lift based on air density, and hot air is less dense than cool air. At sufficiently high temperatures, an aircraft needs greater speed, a longer runway, or a reduced payload to generate enough lift to take off safely. At extreme temperatures, some aircraft simply cannot depart from shorter runways at full passenger and cargo loads, a limitation rooted in basic physics rather than mechanical failure. Airports in Phoenix and several Gulf states have already imposed weight or scheduling restrictions on certain flights during the hottest hours. And Middle Eastern airports have long scheduled a disproportionate share of departures for night, partly for passenger comfort, but partly for precisely this aerodynamic reason. Solar energy and electric vehicles present a paradox worth noting, since technologies built to solve the climate problem themselves require adaptation to a hotter climate. Solar panels lose efficiency as their surface temperature rises above an optimal point near 25 degrees, and a panel exposed to direct sun on a hot day can reach surface temperatures of 65 to 75 degrees, with efficiency dropping by a measurable fraction for every degree above that optimum. This means that on the very hottest, sunniest days, when demand for cooling electricity peaks, solar panels are producing less power per unit of sunlight than they would on a milder day, a counterintuitive but well-documented engineering reality that solar engineers in hot climates are actively designing around through cooling systems and new panel materials with reduced temperature sensitivity. Electric vehicle batteries, similarly, have an optimal operating range, and extreme heat above roughly 40 to 45 degrees accelerates battery degradation while also reducing driving range, since a larger share of stored energy goes toward cooling the cabin. Automakers are investing heavily in battery thermal management systems specifically to address this challenge. Simultaneous heat events occurring across multiple regions at once represent what many climatologists describe as one of the most concerning aspects of the broader trend. The global food system is designed with built-in resilience through geographic diversity, where a poor harvest in one region is typically offset by a strong harvest somewhere else, which is why localized droughts rarely trigger a global food crisis on their own. But that resilience depends on most regions functioning normally at the same time. When extreme heat strikes several major agricultural regions in the same growing season, the buffering effect that geographic diversity normally provides simply disappears. Researchers studying the statistics of simultaneous heat events across major breadbasket regions have found that the frequency of such synchronized events is increasing faster than the frequency of isolated regional heat waves, a pattern linked to large-scale atmospheric circulation changes, including the same kind of blocking patterns and shifts in planetary wave structure that drive individual heat waves, which can produce heat anomalies in multiple distant regions simultaneously because they share the same underlying atmospheric drivers. For global food security, this transforms a manageable regional problem into a systemic risk that cannot be solved by simply redirecting supply from an unaffected region, because there may not be one. Mountain glaciers illustrate the water story on a timescale measured in decades rather than seasons. The Andes Mountains feed major river systems that supply drinking water and irrigation to tens of millions of people across Peru, Bolivia, Chile, and Argentina. Glaciers function as natural reservoirs, storing winter precipitation as ice and releasing it gradually through the dry season, which makes river flow predictable and steady. Right now, Andean glaciers are retreating at a pace that has alarmed glaciologists tracking them for decades, with some smaller glaciers having already disappeared entirely within living memory. The short-term effect is counterintuitive. More water in rivers in the near term, because more ice is melting than usual, which creates its own flood risk. The long-term effect runs in the opposite direction. Once a glacier shrinks past a certain point, there is simply less ice left to melt each summer, and river flow during the dry season begins to decline permanently. Glaciologists describe this turning point as peak water, the moment after which dry season flow starts a long-term decline. And for several smaller glacial systems in the Andes, researchers believe that turning point has already passed. Attribution science has fundamentally changed how scientists discuss the link between a specific weather event and the broader climate. For decades, climatologists were careful to say that no single storm, drought, or heat wave could be attributed to climate change, since climate describes long-term statistical patterns, not individual events. Modern attribution methods now allow researchers to calculate how much more likely a specific event became because of human-driven warming, compared to a simulated version of the same event under pre-industrial climate conditions. For the severe European heat wave already mentioned, researchers calculated that climate change had made the event many times more likely than it would have been a century earlier, transforming what would once have been an essentially once-in-a-millennium occurrence into something that can recur within a human lifetime. Research groups at several institutions now routinely publish this kind of analysis within days of a major extreme event, a practice that allows the public to understand that what occurred was not simple bad luck or an act of nature in the old sense of the term, but an event whose probability climate change has measurably increased. City-level adaptation is already underway in multiple places around the world, and it demonstrates that meaningful responses are possible even while the underlying trend continues. Ahmedabad in western India became one of the first South Asian cities to implement a formal heat action plan after a severe heat wave caused a sharp spike in mortality. A plan that includes an early warning alert system, training for healthcare workers to recognize and treat heat illness, reflective roof coatings distributed to vulnerable households, and public messaging campaigns timed to forecasted heat events. Mortality data collected in the years following implementation suggests the plan has measurably reduced heat-related deaths compared to the period before it existed. And the model has since been adapted by dozens of other cities across South Asia. Athens appointed one of the world's first dedicated chief heat officers, an official role tasked specifically with coordinating the city's response to extreme heat, including a system that names and categorizes heat waves by severity, similar to how hurricanes are named, a measure intended to raise public awareness and improve emergency coordination. Paris has expanded a network of designated cool refuges, including libraries, museums, and shaded public gardens, that remain open and accessible during heat alerts, specifically for residents without home cooling. Reflective surfaces, sometimes called cool roofs and cool pavements, represent a deceptively simple but well-documented technology. Dark surfaces absorb up to roughly 90% of incoming solar radiation, while light-colored or reflective coatings reflect a much larger share of it back. The surface temperature difference between a dark roof and a reflective white roof under direct summer sun can reach 25 to 30 degrees. Cities including New York and Los Angeles have run cool roof and reflective pavement pilot programs, and measurements from a reflective street coating tested in Los Angeles found a measured surface temperature reduction of roughly 6 to 10 degrees compared to standard asphalt nearby, a result based on direct measurement rather than projection. Archives, libraries, and museums face an unexpected and rarely discussed consequence of extreme heat. Paper, leather, textiles, painted canvas, and photographic materials are all sensitive to temperature and humidity. Elevated heat accelerates the chemical degradation of paper and can cause different layers of a painting, paint and canvas, or wood panel to expand at different rates, creating internal stress that leads to cracking over time. Major museums and archival institutions spend considerable resources maintaining stable climate conditions in storage facilities. And during extreme heat events, when power grids face peak strain, the risk of a temporary failure in climate control systems rises, a risk that has already materialized in a handful of documented cases, each requiring emergency measures to protect irreplaceable collections. Fisheries along multiple coastlines are being reshaped as fish follow shifting water temperatures. Species adapted to cooler water move toward higher latitudes or greater depths as their preferred temperature range retreats. In the North Sea, cod populations that formed the historical backbone of fisheries for several countries have shifted measurably northward toward Norwegian and Icelandic waters, and fishing fleets that worked the same grounds for generations now report declining catches in areas their families once relied on for decades. In the Mediterranean, species native to the Red Sea have migrated through the Suez Canal and established themselves in warming Mediterranean waters, some of them invasive predators that disrupt established food webs and compete directly with traditional commercial species. This is not simply a matter of biological curiosity. It represents an economic reality for fishing communities forced to adapt faster than their equipment, skills, and markets can reasonably keep pace with. Even competitive sports, an arena that seems far removed from climate science, have had to restructure around extreme heat. Marathon events at recent major international athletic competitions were rescheduled to cooler host cities or shifted to early morning start times specifically because of heat risk to athletes, with mandatory cooling breaks introduced and athletes using cooling vests between events. Tennis tournaments held in hot climates now routinely pause matches under formal heat policies that allow players a break once temperature and humidity readings cross a defined threshold. These are measures available to professional sport, with resources, protocols, and dedicated medical staff. The situation is considerably more serious in school athletics in regions without air conditioning, where several jurisdictions have introduced formal heat guidelines for outdoor practice, specifically after students suffered heat stroke during training, with some cases ending tragically. Construction as an industry has had to reorganize itself entirely around extreme heat in several regions. In Gulf states, official bans on outdoor work during the hottest daytime hours now apply for several months of the year, shifting schedules to early morning, evening, and night, with materials delivered overnight to avoid daytime heat. Extreme heat also affects the materials themselves, since concrete sets faster in high heat and can crack if it dries unevenly, prompting builders to use set-retarding additives and specialized mixes designed to reduce heat generation during curing. Engineering codes in multiple countries are being revised to reflect temperature conditions once considered unrealistic for their climate zone, an additional cost and engineering complexity that is nonetheless proving cheaper in the long run than building to standards for a climate that no longer exists. Clothing and textile design have found some genuinely useful answers in this challenge. Traditional garments from cultures that have lived in hot climates for millennia, loose-fitting linen and cotton robes, for example, have been shown in scientific testing to outperform many modern synthetic athletic fabrics in extreme heat, because a loose fit creates an air layer between skin and fabric that allows evaporating moisture to circulate, while light colors reflect rather than absorb solar radiation. Several research groups and textile companies are now developing new heat-adaptive materials, including fabrics engineered to radiate body heat more efficiently as infrared energy, and others embedded with microscopic wax capsules that melt at body temperature, absorbing heat and providing temporary cooling at the skin. These are genuine technologies at various stages of development and commercialization, emerging now because the market of people who need to live and work through extreme heat is only growing. Scientists who work with climate data day after day are, by their own accounts, experiencing something many describe candidly as professional concern, not panic, not a loss of scientific objectivity, but a specific unease that comes from watching a data set's trajectory and understanding where it leads. Researchers including Friederike Otto, whose work helped establish much of modern attribution science, and Jennifer Francis, who has spent years studying the connection between Arctic warming and disruptions to the jet stream, have spoken in multiple interviews and public forums about the growing sense of urgency among colleagues who track this data professionally and watch it unfold in close to real time. It matters to understand that the researchers being described here are not alarmists. They are specialists following the data wherever it leads, and the data is currently leading in a direction that genuinely concerns them professionally. They describe a rate of change that has consistently outpaced expectations. Models considered pessimistic a decade ago have, in several respects, turned out to have been optimistic. The gap between projection and observed reality is itself a major source of concern among those who study climate for a living. The volume and precision of data being collected right now represents an unprecedented record of the state of the planet. Thousands of ground weather stations operating for decades provide directly comparable measurements of temperature, rainfall, and humidity. Networks of ocean buoys record surface and subsurface water temperature continuously. Dozens of satellites measure surface temperature, glacier extent, soil moisture, and fire activity from orbit. Hundreds of thousands of volunteer observers contribute phenological records: when specific plants bloom, when particular bird species arrive, when the first insects of spring appear. Wearable devices worn by millions of people now passively record physiological data: heart rate, blood oxygen, sleep quality, becoming an unexpected source of real-world information about how heat affects the body under ordinary daily conditions. Medical databases, agricultural statistics, and electricity consumption records together produce a level of detail about the changing planet that has never existed before. And this is not a picture of one event or one region. It is a picture of a planetary system shifting simultaneously across multiple dimensions at once. Atmospheric temperature is rising. Ocean temperature is rising. Glaciers are retreating. Sea level is climbing. Extreme weather events are becoming more intense and more frequent. Ecosystems are shifting, with species migrating or disappearing. All of this is happening concurrently, and researchers who study this data daily describe the rate of change as showing no sign of slowing. What ultimately matters most from everything covered here is this: heat is not one problem with one solution. It is a condition that runs underneath every other system: food, water, energy, health, housing, transportation, the economy. Heat reduces crop yields, but heat reduces crop yields simultaneously across multiple regions of the world, which transforms a local agricultural problem into a systemic risk to global food security. Heat overloads power grids, but it overloads them precisely when hospitals are already operating at peak capacity, treating heat stroke patients. Heat dries out soil, but dried soil rejects the next rainfall, deepening the next drought. This is systems interacting with one another, producing effects considerably more complex and far-reaching than the sum of any individual consequence taken in isolation. And it is this simultaneous pressure on multiple systems at once, arriving at a moment when those systems are already operating near their limits, that climatologists describe as the central challenge of advancing heat. The human body does not evolve within a few decades. Urban infrastructure is built for a generation and cannot be rapidly rebuilt. Social norms shift more slowly than atmospheric physics. This is the gap between the speed of climate change and the speed of adaptation, whether biological, technological, or institutional. Adaptation is happening. Laboratories are developing heat-tolerant crop varieties. Cities are building green infrastructure, updating building codes, refining medical protocols, and improving early warning systems. But the pace of adaptation is, for now, falling behind the pace of change. And that gap is what scientists describe with the greatest concern. Not the heat itself as a phenomenon, but the fact that humanity is moving into it faster than it is managing to adjust. Right now, thermometers around the world are recording values that were rare or entirely absent from the historical record only a few decades ago. Satellites are tracking Arctic sea ice extent, shrinking faster than earlier projections anticipated. Ocean buoys are transmitting water temperature data that continues to break records. Physicians are treating heat stroke patients in regions that once rarely saw such cases at all. Farmers are losing harvests to heat their family's land has never experienced before. Engineers are rewriting design standards calibrated for a climate that is already gone. Everything humanity built over the past several centuries, homes, cities, infrastructure, food systems, was constructed for a climate that no longer exists in the form it once did. Everything being built today must instead be designed for the climate that is arriving. This amounts to the largest simultaneous reconstruction of every life support system humanity depends on that has ever confronted the species at once. It is unfolding not as a chosen strategy or a deliberate plan, but as a fact, because temperature itself leaves no alternative. The heat advancing across the planet is not a metaphor. It is a physical process leaving a measurable trace in every record humanity knows how to keep. In ice cores drilled from the depths of glaciers, in temperature records maintained continuously since instrumental measurement began, in clinical statistics on heat stroke admissions, in the trajectory of wheat and rice yields, in the surviving area of living coral reefs, in the water levels of lakes and reservoirs, in the number of tropical nights recorded each season. All of these independent records point in the same direction. The trend is not reversing. The rate is not slowing. And what is described today as an extreme event will, on present trajectory, become tomorrow's ordinary baseline. This is what scientists understand. This is what the data shows. And this is what is happening right now, in every location on Earth equipped with an instrument capable of measuring temperature. Mountain ecosystems and extreme heat form a connection that can feel distant to anyone living in a city. Yet, on closer inspection, it directly shapes water and air quality for hundreds of millions of people. Mountains function as the planet's natural water towers. Snow and ice, accumulated over winter, melt gradually through the warm months, sustaining river flow precisely during the season when rainfall is scarcest. This natural mechanism has supported river valley civilizations for thousands of years. As heat intensifies, mountain snow increasingly melts earlier, in spring rather than summer, which means peak river flow arrives during a season when rivers are already running high, intensifying spring flooding while worsening late summer water scarcity. Alpine meadows and forests that anchor soil and regulate slope hydrology are increasingly stressed by extended drought. The earlier disappearance of snow cover disrupts soil temperature regimes, which in turn reshapes plant community composition. Alpine meadows, peat bogs, and high-elevation lakes are migrating upslope as climate zones themselves shift, and species that once lived near the upper edge of their range now find themselves pushed toward summits, with nowhere higher left to retreat. Biologists are documenting changes in the composition of mountain ecosystems occurring faster than at almost any point in the observed historical record. Tourists seeking relief from lowland summer heat increasingly travel to mountain regions, adding further pressure to ecosystems already under climatic stress. And several countries have introduced visitor restrictions on particularly fragile high-altitude sites, specifically because the combination of climate stress and tourism pressure now threatens to damage the very landscapes people are traveling to see. A closed loop in which heat drives people toward the mountains while their presence compounds the very pressures the mountains are already struggling to absorb. Temperature records, considered as a category of evidence, matter less for any single number than for the pace at which records are broken. A record that stands for decades suggests a relatively stable climate. A record broken every few years, or even annually, suggests a system moving outside its historical boundaries. The European Center for Medium-Range Weather Forecasts maintains continuous global temperature monitoring, comparing each new month against every recorded month stretching back to the start of reliable instrumental measurement in the mid-19th century. In recent years, it has not been individual months, but entire consecutive years that have ranked among the warmest on record, one after another. This is not statistical noise. It is a trend, and the trend shows no sign of slowing. How heat-related death is counted is itself a methodological story that explains why official statistics consistently understate the true toll of any heat wave. A death is formally attributed to heat stroke only in direct cases, where a person loses consciousness from overheating and dies as an immediate result of hyperthermia. The majority of heat-related deaths occur through an indirect path. Heat thickens the blood as dehydration sets in. The heart works harder to circulate that thicker blood. In an elderly person whose cardiovascular system already operates with reduced reserve, this strain can trigger a fatal heart attack, and the medical record lists heart failure as the cause, with no formal connection drawn to the heat itself. Heat similarly worsens chronic respiratory disease, contributes to kidney failure through dehydration, and raises stroke risk through fluid loss, none of which are typically classified as heat deaths, despite occurring because heat pushed an already vulnerable body past its limit. This is precisely why epidemiologists rely on excess mortality, comparing observed deaths during a heat period to the number that would ordinarily be expected, rather than depending solely on cause of death certificates. That gap represents the true cost of a heat wave, and it is consistently and substantially higher than official statistics on heat stroke alone would suggest. Public health agencies in multiple countries now track excess mortality during heat events in close to real time, and the resulting data shows heat-related mortality rising not because people have become more fragile, but because the heat itself has become more severe. The medicine of heat has changed in concrete, measurable ways as a direct response to this trend. Several European countries have developed formal national heat response plans, built around early warning systems that allow medical services to prepare before a heat wave strikes, rather than reacting after the fact. The opening of additional public cooling centers accessible to anyone, elderly residents, people experiencing homelessness, anyone without air conditioning at home, and outreach teams specifically tasked with checking on isolated elderly residents during alert periods. These systems exist because earlier heat waves caused mass casualties precisely because no such preparation existed at the time. Today, they activate nearly every summer as routine procedure rather than emergency measure, itself a quiet but unmistakable signal of how much the climate has already shifted. Emergency medical services in several countries have developed dedicated heat stroke protocols, including rapid on-site cooling of a patient rather than waiting for hospital transport, since every minute matters once severe hyperthermia sets in, a lesson learned directly from past cases where time lost in transit produced outcomes that proved irreversible. What remains most important from everything described here is this: heat is not a single problem solvable through a single solution. It is a condition that runs through every system that sustains human life: food, water, energy, health, housing, transportation, the economy. A condition that arrived faster than preparation allowed, and one that continues shifting in a direction scientists describe without exaggeration and without softening. What is unfolding right now is not the beginning of this story. It is already somewhere closer to the middle. And how humanity adapts across the coming decades, in its cities, its farms, its hospitals, its homes, will determine how manageable that middle chapter ultimately proves to be. Insurance and real estate markets are quietly absorbing this shift faster than most public conversation has caught up with. Underwriters who price risk for a living have begun treating extreme heat with the same seriousness traditionally reserved for floods and hurricanes, because heat damages property in ways that are easy to overlook until the bill arrives. Warped roofing materials, stressed building foundations in regions experiencing more frequent drought and deluge cycles, and spoiled inventory in warehouses never designed for sustained extreme heat. In parts of the southwestern United States, some insurers have already declined to renew certain property policies, specifically citing escalating heat and wildfire risk, a market signal that tends to move faster and more bluntly than political or regulatory responses. Real estate appraisers in a handful of cities have started factoring projected summer heat exposure into long-term property valuations, particularly for buildings without adequate cooling infrastructure, treating it as a depreciating asset class rather than a fixed feature of the property. None of this is being driven by environmental advocacy. It is being driven by the plain financial mathematics of risk, which tends to notice changing conditions long before broader public discourse fully absorbs them. Public health surveillance itself is adapting in response to what the data has revealed. Several national weather services have moved beyond simple temperature forecasts toward heat-specific warning systems that combine temperature, humidity, time of day, and even projected hospital admission risk into a single composite alert, an approach borrowed conceptually from hurricane and flood forecasting, where the goal is not just to report a number, but to communicate a level of danger the public can act on immediately. Some cities have begun issuing heat alerts with the same urgency and visibility traditionally reserved for severe storm warnings, recognizing that heat, despite producing no dramatic visual spectacle of wind or floodwater, has quietly become one of the deadliest weather hazards measured by annual fatalities in several countries, often exceeding the combined toll of more visually dramatic disasters like tornadoes and hurricanes in an average year. This shift in how heat is communicated, treating it less like background weather and more like an acute hazard requiring immediate precaution, is itself a recognition by public health officials that the old framing of heat as mere discomfort no longer matches the reality the data describes. The data keeps coming in, the instruments keep measuring, and the heat keeps rising.